Okay, we're recording. So, last time we were talking about how to slice up a three-dimensional solid, right? And there's this process to follow, and you have to kind of cycle through this 3 times, right? One for each of the 3 different directions that you're going to be slicing, because there are 3 directions, because it's a triple integral, because it's a solid. Resulting in then this expression for our iterated triple integral, or a triple iterated integral, I guess maybe we should call it. We talked through that slicing process last time, what it looks like geometrically, and I just want to make a few observations about what's going to happen in the resulting on the resulting iterated integral. For one thing, notice that it goes outside to inside. It's like this. You start, your very first slicing that we did was the X slicing. That was arbitrary, but anyway, whatever slicing you do first is on the outside, and then as you continue to slice, you move your way inward, just like with double integrals, frankly. Note further, when we, for example, look at the range of values of y, you got to remember the range of values of y, these y bounds, right, are relevant to what's happening on an X slice, right? We've already done our X slicing by the time we get into this, you might call it the second slice. So that means that the bounds need to know what value of X you're looking at. That means that these bounds will be a function of, they will be functions of X. So said differently, it's a function of the variable further to the outside, right? So we're looking here at our dy integral, and those y bounds are functions of the x value, because the dx integral is further to the outside. And then likewise, same story for the z integrals. When we were looking at our z bounds, right, looking at our z integral, we went over the starting and ending values of z. Well, it depends on which slice of the slice you're looking at, right? I mean, those z bounds are going to be different depending on whether you're looking, you might say above that point, or whether you're looking at way over here above that point, or maybe over here above that point, something like that, right? So those z bounds depend on both x and y, so they are on the x slice of the y slice, functions then of both x and y. Notice then functions of the variables further to the outside. Okay, so that's the something to always check for, by the way. If this isn't the case, for example, if your x bounds, if you slice in this order, and if you're outside x bounds are functions of y and z, this is not right. Right, it's at a glance immediately, obviously wrong. Right, so don't step on that landmine. Make sure that your dependencies go the way that they kind of have to. Okay, if I can get this all erased. All right. Further note, and just sort of one last reminder, when you're looking at your dy integral, right? Looking at your dy integral, you get to treat x as being a constant, right? So x is a constant because we're fixing a value of x so that for that x we can figure out what's happening in the y direction, right? So for that inside integral, the variables further to the outside are constant. Okay. All right. Let's see here. What have I... here we go. Okay, so and then just like with double integrals, we're going to find bounds by looking at the points that define them, which are going to be identified as being on certain surfaces which have certain equations. And this is highly analogous. It's the exact same sort of connect the dots that we had back with double integrals, and I'm going to demonstrate that by just kind of diving into an example. So here we go. We're going to look at this tetrahedron. And again, we're going to look at sort of a phase 2 only, in the sense that there's some application that led to this triple integral. Let's not worry about that part. Maybe we're computing a mass. Maybe we're computing a amount of work or whatever. Let's not worry about that. And then, of course, there's the phase 3 that when I have an iterated integral, I'll have to plug it into the fundamental theorem of calculus evaluate it. But we're just going to focus just on phase 2, turning the triple integral into an iterated integral. Okay. So, let's do it. For no particular reason, I'm going to do my slicing in this order. Really doesn't matter in this case. We will talk in a few minutes about how to decide which order to slice in, depending on the circumstance, and it's going to depend on the shape of the domain and the nature of the surfaces that define it, and et cetera, et cetera. And again, we'll talk about that later. For the moment, arbitrarily, I'm going to pick this order. So I've got to figure out my range of values of x. There's my x-axis. Here's what x slices look like, right? Perpendicular to the axis in question. And you can see that my first and last slices are kind of there and there. Sometimes it's easy to identify what the corresponding bound is. So, for example, let's look at this lower bound for x. That lower bound for x, this slice, it is the YZ plane. It is where x is equal to 0. So it's kind of a freebie that that's going to be x equals 0. And you get lucky sometimes. Things are just clear. That's nice. Okay. All right. Less obvious question. The upper bound for x. Where is the upper bound for x here? And here's where you have to think through, okay, we've got our point that defines our upper bound because this is that last slice. And what do I know about that point? What geometric objects in this picture is this point on? What can I say about them? What do I know about them? And what does that tell me then about the value of x I'm looking at? Okay, so for example, this point defining x2 that we're interested in, notice it is on this plane here, which has this equation. I'm going to see it from the picture. Thank you, picture. By the way, we've got to have a good picture. Your picture is your guide that will tell you, looking at the picture, seeing which point is on what surfaces will tell you what algebra to write down and work with. So you've got to have the picture to be able to make reasonable sense out of what's going on. Okay, let's see here. Next, I can also tell it's on that surface. Thank you, picture. Surface having that equation. And then lastly, I can see from the picture that the point I'm interested in is on that surface, which has that equation. All these equations were given, by the way, in the definition of the tetrahedron, of course. And these are the three equations that define the point I'm interested in. So in these three equations, I need to solve for x, because I'm interested in an x bound. And now begins the algebra. Right? So solve for x. Of course, you see when you solve for x, you're going to have y's and z's left over. Conveniently, I also know information about y and z. All together, we get 1 as our upper bound. How we doing? Now, a lot of you might say, okay, yeah, but that was kind of obvious from the picture as well. It will not always be as sort of algebraically easy as this. So the point here is not the conclusion. The point is the process. Right? The process of identifying, well, this point is on certain surfaces. Those surfaces have certain equations, and then you can solve for what you want. All right. Moving along. So let's move now to, we're going to fix a value of x. I'll tell you what I'm going to do. I'm going to use green for x. So we're going to fix this x slice. And now on that x slice, I want to move over and let's think about what's the range of values of y. So what do y slices look like? Again, you got to think geometrically, right? We've got this x slices like this, and if I take a y slice of that x slice, what does that look like? And those slices kind of all look something along those lines right there, right? And there we go. So the first slice is there, which is in. Oh yeah, question. Go ahead.
Y slices look like that, and those are Z slices.
One more time. I'm sorry.
Wouldn't like a Y slice look like that, where like This way?
So you got to keep in mind, y slices are slices perpendicular to the y-axis, right? That didn't draw well. So there's the y-axis, right? And so a y slice is going to be, see if I can do this, like that. But you got to keep in mind, we're not interested in the y slice of the solid. We're interested in the y slice of the x slice. And so we've got this kind of thing where two planes are intersecting. Does that make sense? Is everybody happy with that? Okay. Cool. All right. Yeah. So first y slice, pretty clearly right there where y equals 0. Again, sometimes it's easy. Okay. The last y slice, that point right there. Right, as we're going through our y slicing process, that's where we finish slicing up the x slice. All right. So what can we say about this point? Well, I know 3 things about this point. So first, I want to recognize I know what x is, right? I'm on my x slice. X is, well, whatever x is, right? This is going to, what my y bounds are need to depend on x, so I need to know what x is. That is one of the things that I know. And so I like to write that, it seems a little goofy, but I like to write it as x equals x as just kind of a personal reminder that, yeah, don't forget, you know, you're allowed to leave your answer in terms of x. X is known. So I like to put that down there. Now, what else do I know about this blue point? You just got to, again, look at the picture and think through what you know. Picture tells me that it's on that plane. Right? Picture also tells me that it is on that plane. And so here we are again. I've got 3 equations. I'm trying to find a y bound. So in these 3 equations, I'm going to solve for y. And you get 1 minus x. What do you think? Everybody happy? Okay. A lot of students will make this make a mistake on this. A lot of students will mistakenly think, okay, range of values of y. Well, let's see here. Here's my first y slice, and then here's my various y slices, and then my last y slice is over here, and a lot of people will put 1 as the y slices. Absolutely wrong, right? We're not slicing up the solid. We're slicing up the x slice. We're slicing up the slice we've already done. Okay, so that would be wrong. Okay. Alrighty, now looking at our slice of our slice, right? That then meaning that both, let's see here, both x and y are known, fixed, and it's for those values of x and y that I want to find the range of values of z. Z starts here, and again, sometimes it's easy. Sometimes it's just, it's right there looking at you. What's the value of z at this point where z equals 0? Well, it's 0, right? So, lucky breaks happen. What about the upper bound, though? Again, a little bit more worrisome. Now, I do know x, I do know y at this point, but I also need to see from the picture that the point in question is on that surface also. Again, I'm looking for a value of z. So in these equations, I solve for z, leaving z as a function of x and y, of course. And that gives me that. So there we go. Iterated integral. And now, punch it up at the fundamental theorem of calculus 3 times and answer. Everybody see the process? Okay. All right. Now we're going to do a bunch more examples. A couple of bits of advice first. Note that you do have 6 different ways that you can arrange those differentials, 6 different ways, in other words, that you can do your slicing, and that's a lot of options to choose from. It's a good news, bad news kind of a deal. Good news, you got a lot of options. Bad news, you have to discern between a lot of options, right? So, anyway, be thoughtful about it, and here are some of the particulars. Just like with double integrals, try not to slice through corners and edges and stuff. That's going to make bad things happen when you try to find your inner bounds, right? So that's just like with double integrals. If one of your variables is naturally a function of the others in the equations describing your domain, probably want to have that on the inside. Whichever variable you slice on the inside is the one you're going to need to solve for. So how about solving for the thing you've already got solved for? Right? So this is typically good guidance. I don't want to say it's always true, but this helps you avoid inverting functions, which tends to be bad in integrals. So these are the same sort of guidelines that we had for double integrals. There's a new one I want to introduce, and this is the idea of projections. It's a little bit of a weird conversation to have in the absence of an example, so I'm going to actually go through these ideas for what I mean by a good projection in the context of the example here on the next page. So let me start by setting up this example here on the next page, and then we'll go back and talk about the projections. So, okay, there's that bounded by language. So we're going to have to think through what's been described here and then make sure we pick the solid that actually is, that we can put in a box, bounded, right? And whose boundary consists of what's described. So here I have first octant, right? And we've got this plane, z equals 1. And we've got this paraboloid, z equals x squared plus y squared. Right? And what do these various surfaces bound? Well, they bound this, let's see here if I can, it's just this thing here. It's like it's like somebody had a cereal bowl and then cut it in fourths. Right? Everybody see my solid there? Okay. All right. Now, one of the first things I'm going to notice, per this little bit of advice up here, if one of the variables is a function of the others, we want to put that slicing on the inside. And that's the case here, right? Z, pretty naturally thought of as a function of x and y in that equation. I mean, I guess I could solve for x, but if I solve for x or if I solve for y, I'm going to have square roots in my bounds and therefore in my eventual integrands. I don't want, I mean, it's not that you can't, it's that I don't want to, and I suspect you don't want to either. So we're going to put dz on the inside, and let me scroll down to where I've done that. dz on the inside, like that, like so. Everybody happy so far? Okay. Now I'm going to notice that there's what I'm going to call this is where we're going to go out and talk about projections again. I claim there's a good projection to the XY plane. Now, what do I mean by a good projection? First of all, let's talk about a projection. If you've got this solid that we're looking at, right, we've got this solid thing here. Projection to the XY plane means exactly what it sounds like. You just look at the shadow down in the XY plane, right? So I claim that this is a good projection, and again, I need to clarify what I mean by saying this is a good projection. Okay, so looking back up to here, what I mean by a good projection. First of all, the shadow isn't weird. The shadow is a nice shape. Let's look back and confirm here. The shadow that we're looking at, this projection, well, it's a quarter disc. It's not some sort of weird octagonal oddball thing. I mean, to be fair, it does have a curved edge there, and when I slice this up, I'm going to have a square root, but there's really no way to avoid that. I mean, all of the projections are going to have that same sort of some sort of a curve in it. So I'm going to say that this is not a bad projection. Okay. All right. Good shadow. Next, the top and bottom surfaces are consistent and desirable. So let me talk about what I mean by that. Top and bottom surfaces says, all right, if I'm looking at a point down here in the projection, like that point there in the projection, and if I look up from there, I get there's a sort of a what you might call an XY slice, right? And we're going to talk about the points, the starting point of that slice, and then the ending point of that slice. And what I mean by the bottom surface is, I mean the surface. That's no good. The surface that point is always on, and that point is always on that surface consistently. Right? So no matter which point you look at in the shadow, any point in the shadow, when you sort of go straight up from there, what's the first surface that you hit? It's always this purple paraboloid every time. And that purple paraboloid's not bad. I understand it. It's always the same. This is what I mean by consistent and desirable. Right? This is the bottom surface that we're looking at here. Right? And then I claim the same is true of the top surface. The top surface here, that ending point, always on that same plane. So the top surface, consistently, always on the same surface, always the same equation, and desirable in the sense that, well, it's got a nice equation. There's nothing creepy or weird about this. Everybody with me? So this is what you want to look for. This is what defines to me a good projection. If I can get this to erase. There we go. A good projection means the shadow is desirable, the top and bottom surfaces are consistent and also desirable. So now, what do you do with this? What we do with a good projection is if you're slicing in such a way that those two variables, whichever variables correspond to the projection you're doing here, we are projecting down to the XY plane. So X and Y are the two variables in question. If you put those on the outside, notice, by the way, good news, we are. We've got X and Y on the outside. Right? Then here's the wonderful punchline. And the whole reason we like projections in the first place is that you can just look only at the projection, and the projection itself will give you the bounds for those two outside integrals. Let's see that happen. Let's start slicing up. Now I'm going to do this two different ways. I'm going to do this sort of the old-fashioned way first, where I slice up this solid like we slice up solids. And then I'm going to point out that, we didn't have to, because we can see all the relevant information from just looking only at the projection. So here we go. Y slices. Here's what our Y slices look like. There's my first Y slice. Here is a generic Y slice. And here's my last Y slice. So sure, I could take this three-dimensional picture and slice it and draw it. No, but by the way, I don't know if you recognize this, but this is a hard picture to draw. All right, it's three-dimensional, it's challenging. I did it, right? But this took me a while to be able to draw. Yes, you can do it that way, but notice the values of Y that I get when I slice up the solid, exactly the same as the values of Y that I would get by slicing up the projection. Because the only difference between the projection and what it projects down to, from the solid and its projection, the only difference is that I'm ignoring the Z coordinate. The Y coordinates don't change in that projection. So the range of values of Y on the projection, exactly the same as the range of values of Y on the solid. Then likewise, if you pick a slice, now again, our Y slices look like this. y slices of our projection look like that. Let's talk about the range of values of x. Well, the x slices of my y slice look like that. The x slices of my y slice of my projection look like this. And those are all the same x values. Right? The range of values of x on a thing sitting up here, well, if I ignore z, if I just lose the z and view them down here in the xy plane, I didn't change the x coordinates at all. So again, you get the same values. So I don't need to look at this complicated picture up here. I don't need to slice up that picture. I can instead just focus on what does the projection look like, projection into the appropriate coordinate plane, understand just that. It's basically a double integral problem at this point. It's a two-dimensional picture. It's really easy to draw. You save yourselves a lot of artistic challenge. And with double integral arguments, there are those bounds. And we are 2/3 of the way through this triple integral, and we haven't even hardly looked at the three-dimensional picture yet. Right? Just by looking at the projection alone, we can identify those bounds. Everybody see the point there? This is a really nice trick. Yeah, go ahead.
Why do we set z equal to 1?
Oh, I have. Okay, yeah, sure, fair. Okay, so the one little bit of work that we do have to do to figure out these bounds, I do need to understand this curve, right? And so, question: where does that curve come from? Well, it's part of the projection. So it's the projection of a certain part of this solid, and in particular, it's the projection of this curve. That curve, I claim. Let me just clean up my mess here. That curve is the intersection of that surface and that surface. And this being the intersection of those two surfaces, I want to know where both of those equations are true. And if both of those are true, then we get that equation right there. Is that cool? Yeah. So I mean, you do have to look at your three-dimensional picture to make sure that you have a clear understanding what the projection looks like, but you don't have to slice up your three-dimensional picture. Okay. Alrighty, so we're 2/3 of the way done. We have our x and our y bounds identified, and now for a given value of x and y, I mean, the only part of the three-dimensional picture I have to really look at is to figure out, okay, well, where on that x slice of that y slice, where does z start? Where does z end? And conveniently, we've already arranged that this starting point is always on the same surface. This starting point is always on that surface right there, and so solving for z is easy. Right? And likewise, the ending point here, always on this same surface. And so that ending value also going to be easy to solve for. Everybody on board? Yes?
Once we establish we want dz to be
I'm sorry.
Once we decide we want dz to be the most inward thing,
Yeah.
is the order of dx and dy arbitrary at that point?
Great question. In this case, it's pretty arbitrary, but it's not always, right? It depends on the nature of what the projection looks like. You effectively have a two-dimensional domain. You basically have a double integral slicing problem, and so you want to look at that projection and think, on that projection, am I going to slice through a corner? Am I going to, would I like to view y as a function of x more than x as a function of y? And of course, you see from the algebra, it really doesn't matter in this case, right? But in other cases, absolutely. Yeah. All right. Okay, here's another example. Now, again, you can do this either of two ways. We're going to, our domain here, you notice, is the solid unit ball. Right? highly symmetric, so it really doesn't matter which way you slice it. No particular reason, I guess just because I can. I'm going to arbitrarily choose to do it in this order right here. I encourage you to try it in different orders, right? Just as you got 5 other options, right? So maybe pick a couple of them and think them through. So again, you can do this 2 different ways. You can think about what does a slice of your solid look like. Think about the first and last, right? We're doing X bounds first. Well, what's the first and last X slice? And then you can look at that X slice and then ask, what's the range of values now of Z? Well, our Z slices look like this. It's kind of hard to see on that picture, so we come over to here. Your Z slices look kind of like that. You can think about where the first and last Z slices are. You notice the pictures are getting a little hard to draw, right? So, not that you can't do it that way. And I think it's a good little bit of mathematical weightlifting to go ahead and try this way. Think, can you struggle with the drawing. Try to get to where you can draw this reasonably well without making your picture too cluttered. This is all healthy exercise. But it's a lot easier to think about it from a point of view of projections. Because it's pretty immediate, for example, to notice that if I look in the XZ coordinate plane, what is the projection? What happens when I smush this solid into the XZ plane? I get a disk, right? 2-dimensional disk. It's easy to draw our 2-dimensional disk here in the XZ plane. Let's see. I'm just going to draw it over here. It's boom. There it is in the XZ plane. And you can slice up this disk in the XZ plane however you like. Slice it up, the usual double integral sort of way. Not a hard picture to draw, and now we're 2/3 of the way done. Just by looking at what it was an easy projection into the XZ plane, right? So the last remaining question then is to figure out for a given why am I erasing that? I'm going to leave that. For a given value of X and Z, so, for some X, some Z, where does Y start and end? Well, Y starts at that point, Y ends at that point. And the good news here is both of these points on the sphere. And again, pretty clear to see they're both on the sphere, right? So solve for Y on the sphere, and you get plus or minus of those things. So I think taking a projection point of view on this question makes it a lot easier. Now again, if you want to, and I think a good mathematical weightlifting, give it a shot. Try to slice this up the usual way. It's pretty hard to draw. This is another one that took me a while, and I think I was less successful with this picture. It's just a harder picture, I think. Right, but healthy exercise. Struggle with that, gain some art, mathematical drawing skills, and there you go. Yes.
A little bit confused with the picture. So B is like the smaller ball we have.
So B is the entire unit ball. It's this whole solid. Right, that's our domain. Right, and we're slicing up that 3-dimensional solid ball by looking at its projection, which I have in dark blue, and then the resulting Y range in green there. That make sense? Okay.
Oh, I see.
Yeah. Okay, cool. All right. Okay, so next example. This is a weird one. Now, I've got the picture drawn for you right here. But a very reasonable question would be, how do I take these 5 equations of planes and produce that picture? Right? And I'll say in general, if you take 5 random planes, very hard problem. Oh my gosh. How do these 5 planes intersect? Which ones? It's a hard problem. right? If you have 5 random planes. So very importantly, these are not 5 random planes. So there's a nice little foot in the door, and to note that 3 of these equations don't have y in them at all, right? So no y's, no y's, no y's. So reminder, we talked about back in chapter 1, this is first week of class, this is a long time ago to be fair. But when you have an equation that doesn't have, let's say, the variable y in it, the resulting surface is parallel to that y axis. Hope you all might remember that discussion. Again, it was a long time ago. So that means that these 3 planes are all parallel to the y axis, which means that I can understand them just by looking, for example, in the xz plane, and z equals 0, boom. Z equals x, fine. X plus z equals 2, sure. If I can get that, there we go. Right? And so just by looking in the xz, I know this is all going to be parallel to the y-axis, and I'll drag it parallel to the y-axis once I've understood what's going on here. But I can see very clearly, just by drawing these lines, what the cross-section of these 3 planes look like. And it's a little triangle there. And so I can then extend and say, all right, well then, I'm going to start off by looking at this, what we call that, prism. Right, so these 3 we're 60% of the way done with our picture now, and all benefited from one trick there. Okay. Now you do have to then fill in the blanks. So y equals 0. Where is y equals 0? Well, that's this. Like that, how does this plane y equals 0 intersect our prism? Well, it intersects like this, right? And then I also have to, and this is the annoying one, I have to think about this plane. Oh gosh, how does that intersect? And this is, there's x plus y plus z equals 3. It's kind of coming in and slicing at a weird angle, and so that's going to give you a cross section that's also at a weird angle. Like that. There we go. And so then all together, you see we have the prism. It's been sliced in these 2 ways, one weird, one not weird. And as a result, we have that picture. Okay, so it's a tough little artistic challenge. Keep in mind that questions that I'll be asking y'all on exams and homework and stuff like that are tempered by, they have to be doable. Right? They have to be reasonable in some way. So I'm not going to give you a question where there's 5 random planes that don't have, where there's no nice foot in the door. Right? But do be aware, do be on the lookout for the possibility of something like this where, there is that foot in the door. And again, notice no y's. And that's what allows you to sort of get started on the picture. Okay, now with that in mind, how do we slice this thing? Again, 2 different ways that you can think about this. You can actually slice up the solid, right? Actually take your solid and be like, all right, well, here's what y slices look like. And then you can slice your slices, etc. What I've drawn here would be a bad choice, though, because you notice I'm going to slice through a corner right there, mid-process, after which point my slices start to look different, and furthermore, my slices get harder to draw. So I'm going to take a whack at it here. I think my slices would start to look like... I've done better. Anyway, but something like that, right? This angled plane over here is going to start chopping the ends off our little green triangles, right? So when I start doing my x and z bounds, the x and z bounds for this blue cross section is going to be qualitatively different than for the green cross sections. And so we slice through a corner, bad things happen, and so we don't want to do that. So you can play different sort of approaches here. You can take X slices. Oh, what did I just do there? Oh man, something is not right. Let me try that again. Okay, X slice. Like that. Next X slice. Oh, yeah, there it is. So my X slices might be something like this, but then, of course, you notice corner. I'm going to slice through a corner again. Again, bad. We don't slice through corners if we can possibly avoid it. So if you try all the different approaches, in fact, there is only one of your 6 options that will allow you to slice without ever hitting corners. And that's another good little mathematical weightlifting, good little sort of geometric exercise. Think through what those slices look like. Again, it's hard, right? Right? But it's good practice thinking three-dimensionally. Alternative. You can instead think about projections, right? And you notice from the picture, this projection over here is pretty nice. It's just a triangle, and furthermore, the sort of the lower bound surface is always that plane. Everywhere in that XZ projection, always that same plane. The upper bound surface, always this surface. There. For every point in that XZ projection. So we've got a nice shadow. We've got a nice, consistent, desirable lower surface and upper surface. That's a good projection. And if you just take this projection point of view, then, from the projection point of view, XZ on the outside, because we're projecting into the XZ plane, right? We can just take that green triangle and just slice it up in two-dimensional analysis, right? You could in fact draw this triangle on the XZ plane, two-dimensional picture, literally. Easy bounds. And then you notice that your lower Y bound is 0 because of that plane. Your upper Y bound is this because you can solve for Y on that surface. And again, easier approach. Sometimes the projection helps more than others. So it's a tool for your toolbox. I think it's pretty useful in this case. More in some, less in others. Here's one where it really helps tremendously. Here we've got, again, 2 surfaces. We've got this surface there. That paraboloid. Flashbacks to chapter 2 to figure out what surfaces like that look like. Make sure you're good at that. You can't slice up the solid if you can't draw the solid. Right? So make sure you're good with all that chapter 2 stuff. Here's our other paraboloid. Something like that. And man, if you start slicing this thing up, bad things happen. For example, let's see here. Let me go back to so if you slice perpendicular to the y-axis, your slices look like that until you hit this point there, after which your slices are annuli. Right? They're little washer kind of shaped things, right? So something bad happened here, qualitatively different on either side. If we did our dy on the outside, we're going to have to break it up into 2 pieces. And furthermore, slicing up the slices over here, other bad things happen. Right? So this is a highly undesirable choice. Notice further, if I were to slice a different way, let's slice dz first. I'm going to try to draw this, but my slices, oh man, this is a hard drawing to do. Our slices are something kind of like that. Hard to draw, hard to visualize. Not that you can't do it, but, tough. And I don't even particularly recommend that you try to. I think this is getting to be too challenging even to be good practice. So let me just say, be satisfied with this being a bad choice. Right? But we take a projection point of view, right? If I look at the projection over here into the the XZ plane, right, I have a good projection, nice shadow, it's just a disk, nothing weird. My lower bound surface is always that one. My upper bound surface is always that one. And you gotta go through and figure out what what's the boundary of that disk. Well, it comes from this intersection over here. That intersection is where both of these equations hold. Blah blah blah. Right? A few details we pounded out, but ultimately you're slicing up a disk, and then you're going from the blue surface to the green surface, and slicing up the disk. Gives you your X and Z bounds like that. And then blue to green gives you those bounds there. Everybody see the strategy details? I'm going to let y'all look through on your own, but that's the big picture strategy. So in this one, the projection strategy is borderline indispensable. Right? Much, much easier. Okay, so that's 5.4. We're going to say a couple of quick words about section 5.5, change of variables. By the way, this is another one of these massive, enormous sections that honestly, if you were to break it up into 2 sections, it would be 2 still fairly big sections. But it's one massive, huge section. So anyway, it's going to take us a long time to get through 5.5. I want to segue into this idea of this method called change of variables, which, by the way, is enormously important in multivariable calculus. It's a big deal. It's going to take us it's a lot we can do with it. A lot to say. I'm going to segue by pointing out that it's really just an extension of the substitution rule from single variable calculus. So I'm going to make a couple of quick observations about substitution rule. I'm going to give you a point of view on the substitution rule that's going to seem pretty weird. It's arguably something you've probably never seen this point of view on the substitution rule before. Again, the purpose is to take a point of view that will allow me to then extend to a multivariable setting. And when you extend this point of view specifically, we will get the substitution rule. Okay, so here we go. Here's the substitution rule that I'm sure y'all have seen before. It's written as an equation. You've probably seen it previously as a method or here's what you do. It's a strategy or something. But written as an equation, this is it. This says if you have the equation, g of t equals x, and you can plug that in and turn one integral into a different integral. Okay. All right. So the point of view I want to take on this, usually this is thought of as an algebraic thing. I want to think of this kind of geometrically, at least partly geometrically. I want to think of g as being literally a function where I've got the t-axis as my domain and the x-axis as my target. And then I want to think about what's actually happening to these integrals. Like, how am I turning one of these integrals into the other of these integrals? And there's, in some sense, kind of 2 steps in this. The first step is what I like to call the pullback step. Let's see here. Let me do it like this. I'll do this in blue. The pullback step. So there's this weird thing about how functions work. The obvious part is if you have a function that goes this way, well, then points go from there over there. Points go the same way the function did. You give me a point in the domain, out comes a point in the target. Points go forward. You might say that the function pushes points forward. Okay. But expressions get pulled back. Expressions go the other way. Because notice if you have an x, if you have an expression of x, right? So there's my x. When I plug in this formula, well, I had some big expression involving x's, and then I plugged in. Now, I've got some great big expression involving t's. Right? So, a value of t turns into a value of x, but an expression written in terms of x pulls back through the function, you might say, to turn into an expression involving t's. It's just how the phenomenon of plugging in works, right? When you plug in an expression in terms of x turns into an expression in terms of t. And it's backwards, right? It goes this way, opposite of the direction of the function. Everybody okay with that? Okay. And there's another half of the point of view here that I'm not going to have time for. We're already out of time. So we'll draw the line right here for today, and see y'all later. Hope you all have a good weekend, and see you on Monday.